Okay, so we've got the following claim. F is a map from D to D dash, and D is open and D dash is open in C. Suppose that F is analytic on D, right? It's holomorphic on there. Suppose that F is a bijection, then I claim that F inverse, which I know exists because of this, is also analytic on D dash, going the other way, right? So this is quite a strong condition, right? So what's the proof of this? So I use the inverse function theorem. Okay, so the inverse function theorem. What does it say, the inverse function theorem from complex analysis? Okay, so it says that, so the second part that we really want to use is that if F is injective and that F dash of Z is not equal to 0 for all Z in D, then its image is open, okay, and the inverse is analytic. Okay, so every point where F, the derivative, is not equal to 0, you've got a neighborhood at which you restricted to it, you have a diffeomorphism, right? And so that gives that tells you why it's an open mapping, because the inverse in particular is continuous since it's analytic, right? Sort of remember this from manifolds as well, okay? So we use this property, right? Okay, so how can we prove this, that it's analytic on D dash? Well, we have that F inverse is analytic on the set D dash minus Z in D dash, Z in D dash, such that F dash of F inverse of Z is equal to 0. Right? So these are just points in D, right? But the zeros, of course, of finite order, but we don't really have to say this, it's implicit that we're talking about finite order, of an analytic function are isolated. Okay? So F inverse is analytic on D dash minus a bunch of isolated points. Okay? But okay. So what, okay, we're saying zeros of finite order are isolated. So that gives us a contradiction, right? Okay, I'm thinking of a quick way to see that it's a contradiction. Right, so we kind of want to intuitively say, okay, the function is, the function has zero derivative here, right? But, on any point, so since this is isolated, right? So this is the picture that we have, right? Let's say that this is a point that belongs to here, right? Now, this is a 0 point, but there exists a delta such that within this ball, F dash is never equal to 0 except here, right? So that means that any point I pick here that's apart from this, so any point I pick in this punctured disk, will have a non-zero derivative, and so I can find a neighborhood at which F dash, F inverse is analytic, right? Well, it's a little bit, it gets a little bit messy if you overthink this, but the key to this is Riemann's, so the key that unlocks this is Riemann's removability theorem. Is that what it's? Yeah, removability theorem condition. Okay. So this says that F that maps from D to C, where D is open. Notice I'm not requiring it to be connected. is where F is holomorphic on D apart from Z0 is removable. So that in this case, actually, our F here would be F inverse, right? Because F inverse is analytic on all of these points. So in particular, that this set right here, which I call S, will be a discrete set of singularities of F inverse. I claim that S contains only removable singularities, and the Riemann's removability theorem helps me do that. Okay, so yeah, so this is removable if and only if there exists a punctured neighborhood of a point where F is bounded. So all we have to do is just check that F inverse is bounded on such punctured disk, right? Well, that's then pretty easy to show. I'm going to skip that bit.